More talking? I can talk about anything.
No, we're good.
All right.
So, welcome to NightHacking at DevNexus. My name's Stephen Chen. I run the Oracle Technology Network, and I'm joined by Stuart Holloway. How are you doing, Stuart?
I'm doing great, Stephen. Thanks for inviting me.
And we were going to chat a little bit about Closure Spec. So can you tell me quickly what Closure Spec is?
Yeah, so Closure Spec is a library that's integrated into Closure for specification and testing of programs.
Cool. And so how does Closure Spec compare to like unit testing as an example?
So what Spec allows you to do, let's start with typing, in fact, like something like static typing. So,
static typing.
Static typing would let you make structural statements about something, right? This has this shape, it has these things in it, and so forth. And Spec starts there, but it also allows you, because it's dynamic, it's actually executed during a running program, or can be. So it's not something that it's limited to things that you know at static time, right?
Cool.
So it can actually, it can say those kinds of structural things, but it can also say, I'm going to run this code, and if it returns a Boolean true, then that also contributes to passing the spec, or failing to pass the spec. So you can really say arbitrary things. When you define a structural spec, you get automatically the ability to generate example data that conforms to that spec. So spec uses another Closure library called test.check, which is a port of Haskell's and Erlang's quick check, that idea. So Closure has a similar library, and when you define a spec for a piece of information, then you can generate arbitrary examples of that information. You take that a step further, and you can actually define a spec for the inputs and outputs to a function, and once you've done that, spec will write your tests for you.
I see. So it kind of generates test data, you're testing the inputs and the outputs, and then you can actually run that as, for example, a unit test.
That's right.
To verify your code.
And unlike unit tests, once you have this up and working, a unit test, you write one and you have one, then you write two and you have two. With this, you get it up and running once, which admittedly is probably harder than writing one unit test. But then you have as many tests as you want. Because you could say, run the generator and generate 1,000 or 5,000 or 1,000,000 example invocations of this.
Okay, and then I'm assuming you can kind of capture specific input-output combinations you want and rerun those to verify that nothing's changed in the code?
So one of the ideas with these generator libraries is the use of predictable seeds.
Okay.
And so with the predictable seeds, you don't actually have to capture.
I see.
All you have to do is say...
You just rerun it with the same seed value, and then you'll get exactly the same random data out.
That's right.
And then you can repeat the same unit test without getting different failures out on successful invocations.
That's right.
That's pretty cool.
So, and then, of course, the other thing, there are other things that you want. And so what will happen when you do this kind of testing is you'll generate a failing case where the data that demonstrates the failure is large.
Yep.
And so if you had written a unit test, you would have never done a large example to begin with because it's too hard to write as a person. But now you have the kind of reverse problem, which is you have a large example and it's not even obvious on inspection what's wrong with it, in some domains. And so what libraries like Spec do is heuristic shrinking. So it'll say, I have found a big thing of, say, complexity 75 by some measure, right? Maybe it's a collection that has 75 elements in it that causes a test failure. Can I find something of size 74? Can I find something of size 73?
Yeah.
And so, and there's a famous story that John Hughes tells about this, where he was brought in, not with Closure, but with generative testing. He was brought in to test a NoSQL database to see if it actually delivered its various, semantic guarantees. Yep. And the first test he wrote detected a problem, and then it shrank it down to a single invocation demonstrating the problem. So shrinking is a powerful component of this. Another piece that's important is when a piece of data is incorrect, being able to know what about it is incorrect. And so if you have a complex piece of data that you built up where there's a spec that refers to a spec that refers to a spec, then you can get back just a Boolean, right? Am I good or not? Do I actually conform to the definition of a valued customer in the system? But you can also say, in what way do I fail to conform to the definition of a valued customer? And it will say, well, you're supposed to be a part of an org that has a this, that has a that, and you don't. And that data could then be used to drive user interfaces. So you could do something like where a statically typed language, can put a red squiggly underline underneath a program that's broken. We could actually put a red squiggly underline under a piece of data
that's broken
that's
in a UI.
broken in a UI.
That's pretty cool. So
and then-
actually using it as like runtime feedback to a user.
That's right. And then you could have a back and forth where, and in the development cycle, you could say, hey, I see this is broken. Generate for me some data that would make it valid again and keep going. It's unlikely that you would do that, in your data of record system. But as a development, the back and forth interplay.
Yeah, so that's
between-
probably a helpful debugging aid. So if you can see what the conditions are for passing, it's
Right.
easier to diagnose why it's failing for those
Right.
other cases.
Right. And then there's a flip side to it that's a little bit less obvious, which is you can find out how a thing passes. So how a thing fails, it's like, well, of course, there's a piece over here that's not right. That's how it failed.
Yeah.
But you can have Boolean logic in specs. So you can say something matches this spec if A or B or C is true. And then you can call conform, and conform will return a data structure that says this matches on branch C, as
see.
opposed to matching on branch A.
So they'll actually decompose your spec and then tell you exactly which part of the spec it's failing on.
Right, and so you could use that feature. I mean, this is a feature that you would use not even in testing, like in your programs where you might have written your own sort of if-then-else type
Yeah.
logic to say, if I'm a frequent flyer, go this way. If I'm an ordinary traveler, go that way. You could conform the spec and then, drive polymorphic dispatch off the conformed spec or something like that, where you capture all this domain knowledge in a declarative way instead of encoding it imperatively
Cool.
somewhere in your program.
So what's the overhead if you're running this in your application on like live data and things coming through?
That's a very good question. So a couple-part answer. The first thing is that for generic data manipulation, spec is designed to be as fast as handwritten things. Now, it's not going to be as fast as a hand-tuned, highly optimized thing, but in general, we are finding that there are all kinds of places in programs where you're doing validation, where you would absolutely want to replace your handwritten code
with a spec
because you're not getting any better performance out
So
of
for
that.
basic data validation purposes, it's probably equivalent to handwritten value-by-value checks.
That's right. And obviously, you get a lot more value from it because with those handwritten value-by-value checks, you often get something like, I failed on line 7, as opposed to, here's a nested data structure that shows you exactly where the problem is. Now, when you turn over to testing, of course, there's things you can do that are expensive that you might not want to leave on all the time. So spec includes a testing facility called instrument, where you can say, given a set of function symbols, instrument them to use specs to validate their inputs. And then you could run your test suite with that instrumentation or some subset of it turned on.
Okay.
So it's entirely a la carte in that sense. In fact, not that this is typical, you could actually write specs and never have them execute in any way. It's likely that they would just be wrong, if you haven't actually tried it. But there's nothing, so the act of writing the spec is entirely separate from attaching it to a
you don't get
validation
any
exercise.
overhead from writing a spec, and you can choose whether to run it at runtime, whether to instrument it and run it as part of a test suite.
That's right.
And how you actually want to utilize it.
Right, and the other thing you can do is you can spec the same data more than once. So you can say, I'm going to validate this against an inexpensive spec at the door of my web service.
Yeah.
And during an exhaustive test suite, I'm going to validate it against a much more rigorous specification of the same thing that's you've decided is costly and that you don't want to do everywhere.
Okay, that's cool. And when you're defining specs, how open-ended is the language for defining specs? Is it actually itself a Turing complete language, or
Absolutely, specs are Turing complete because they can call out to arbitrary closure code. So that being said, it's valuable to be thoughtful about when you're leaving the declarative subset, because that declarative subset is going to be more portable, what have you. But yet there are definitely people who are already doing things like, hey, I wrote a spec that depends on this code, so I want to make sure that code's installed somewhere else where that code is going to run.
Okay, cool. And probably some of the features you were mentioning, like being able to figure out which part of a spec fails, are dependent upon it being declarative versus executing arbitrary code?
So when you add an arbitrary predicate, it can't go inside that and tell you anything else. So if I say that an item in inventory has to have a SKU, and the SKU has to match a predicate, which is a regular expression that is the shape of SKUs in our system, then it can't get deeper than the predicate. But it can say, you had a predicate, its name was SKU.
And it failed.
And it's what failed.
As
and then
part
you
of
can,
this long declarative
right.
statement.
And that could be nested, inside of a collection.
Okay, that's very cool. So this is a quick lightning overview of specs. It sounds really exciting. How can folks find more information if they want to give it a try?
So the easiest way is to just do a Google search for Clojure spec. It's spelled SPEC
Yep.
and lowercase. And the first Google hit is the rationale, which talks through some of the motivating problems, and we haven't covered all of those here, that led to the design of spec. And the second Google hit is the spec guide, which
Nice.
is a step-by-step tutorial at a REPL where you can work through using a spec and see what that's like.
Okay, so actually do a little REPL, get some examples, and give it a try.
Right, and somebody has already, as is the case now that we have ClojureScript, as soon as anything cool comes out, somebody will make a web page where you can actually run the code in their web
Nice.
page. So you could also, if you don't want to install Clojure, you can also just go to a web
Yeah.
page. Someone's done that. You should be able to find that as well.
Cool. Yeah, and that just translates to JavaScript and runs in the browser.
That's right.
Nice. Okay, thanks a lot, Stuart. Appreciate the short interview here at DevNexus.
It's my pleasure, Stephen.
And join us for more interviews. We're live streaming the rest of the day, and we'll be streaming from the live stage with great speakers like Baruch, who's in our audience.
Hi.
All right, thank you.
Thanks.